And I got to the IT guy in here. I didn't have the audio on the speaker right. I had it plugged in so it wasn't audible. I was into that. Okay, so we're at we're 101, October 8th, 6th week. Got an email about doing this Tuesday, and took a look at chapters 5 and 6. And Dr. Layton has finished what he's going to go through on chapter 6, so he encouraged me to encourage you to ask questions today. Anything you want to ask or talk about concerning the prior readings, the problem sets, topics of concern, or stuff you want to talk about. So we're going to be pretty open today. Got a couple things in mind to go over to kick things off, unless you got something off the top of your head right now. When does your test open? Your next
right after class.
That opens today, and that covers chapters. Well, that's what I was going to do. 5 and 6. Let's look at this. Now, if I get back here again. Takes a bit sometimes. There it is. So chapter 5 is coal. I apologize, I didn't get the video, all the videos. You guys were here, so it's not that big a deal to you, but the folks that are distance learners, I finally got the other 2 videos posted last night, yesterday afternoon, from last Thursday, and then currently, geez, there we go, put our finger off there. Currently we're into heat to motive power, pretty interesting bunch of topics for me. I was around it pretty much. We at the pulp mill again, we produce steam off of a little bit of natural gas, hog fuel, which we either and sawdust we either purchased or we got as residuals from our own wood classification systems, our wood screening. And the good chips would go to the digesters, and the digesters were different kinds and different size, thickness, and width and length chips would go to those digesters depending on which ones they were. And then we at one time had a sawdust digester, but it used a lot of chemical for what you got out of it, and as economic conditions changed, we burned that sawdust too, and then the real fine stuff we burned. The overs, the great big chips, would go to re-chippers, and a lot of that you couldn't use and would go in with the hog fuel. And of course hog fuel a lot of it came from bark, from the outside of the logs that would go through a debarker before we chipped it. Bark in the pulping process is a no-no, tough thing. It doesn't cook adequately. Your chemical can't attack it right, knots and bark. So, and then we purchased our own hog fuel from the mills that were around the region during that time, produced steam. And then the cooking process, where you're taking chips and putting sodium hydroxide to it, caustic, and salt, just simple sodium sulfate with it to soften that severity of the cook, would pull the lignin out of the wood, and you'll get into lignin a little bit later, but it's got a lot of organics in that lignin. The inorganics would come with it, and of course we tried to save the cellulose in the wood. It wasn't perfect. You did some damage to the cellulose, and you brought a little bit of the cellulose in with that material. But that off material, that lignin material, was called black liquor, and we would concentrate it and burn it. And in burning, the inorganic constituents would change phase and go back in through a recycle process where we'd make more cooking chemical. Okay, you'd lose some, but we recovered over 93% of our original cooking chemical through that process. And it's a craft pulping process, been around forever. But of course the organics in there would burn, and we'd get heat out of it, and in a boiler, and that heat would produce steam, and that steam would go drive, along with the steam from the wood boiler and a little bit of natural gas, would drive processes around the mill, motors, or, not motors, pumps that were driven by turbines, great big ones, blowers, and electrical turbine generators. So we produced about a third of the electricity we used ourselves through that process. So I'm pretty familiar with turbine generators, boilers, and combustion process, and you get into that pretty good here in the heat motive power chapter. So, any questions about any of that? I could go into more detail, but it's probably not worth it. So that process produced heat. And you saw through your coal and this chapter both that this idea of burning a fossil fuel or a tree, wood, to produce energy for heat originally in different ways, that coal to homes, off gas from big coal, coke manufacturing facilities for town gas and whatnot goes back a long ways. And then the initial turbine generators were talked about in your book, the initial turbines and how that has progressed through time. And way back, steam was how you ran your motive machines. You ran ships with steam from coal. You ran even cars from steam in the way back when. Okay, do you have any questions? If not, take a look and see what you might have, and I'll dig some things up we can go over that may be of interest to you, or I can give you some choices. Let me pause the recording here, and I've got a couple places we can go, and I'll give it. Okay, we're looking at problem sets, and decided to go back and take a look at the document that lays out what's expected of the student when he does the problem sets, and what's behind these things. You know, what struck me when these things were formulated was you get into a work environment, and even and you've probably all been there, basic work environment. There's some folks, employees, have real difficulty following instructions. They might be pretty simple, they might not be so simple. If they're not so simple, bringing a notepad isn't that dumb, even to the most basic of a job. Can you follow instructions? And there are times you go into a job and you get trained primarily by written word. Ideally you get showed how to do something, you get told how to do it, or you get to read out how to do it, they show you how to do it, you get to do it with them watching and repeat. Not always the case. Sometimes you have to read and discern and then go do it, and then kind of ask later if you get the chance. So I think it's a part of learning that's pretty important, is to be able to decipher a bunch of composition, a bunch of words, down into something understandable, and say, oh, that's what I got to go do. I can understand it, or go try to do that, or go back and look, say, hey, well, that's what that meant, as you start to get into it. That's part of the reason for these word problems, okay? And I'll read it. The course includes assignments of word problems that will enhance the student's ability to break a problem or situation down to its basic parts and initiate solution. When I got into my first work as an engineer, I had no idea, and it took me a while. I wasn't very good, but the ability to find a way to start solving a problem that you're dealt with, you're asked to do something, and it's not easy to do. You just don't run out and know how to do it right away. You haven't been there, or even if you've been there, you haven't done it before. How do I get this done? And you run across a stumbling block. Well, you got to look at a different avenue just to get it done. So the purpose of the assignment is to allow the student to increase understanding of the physics and quantity of energy in its processes. And Dr. Layton probably spoke of it. This course and 102 and the whole curriculum differ itself fairly dramatically from other environmental courses or sustainability courses in that we try to quantify things. A big part of what we're trying to do here is give you a overview, a view, a idea of what we're up against, what quantities are. And we had an sample problem last week that I think kind of showed how that can be done, where you got a solar system out there and you go, man, that's making power, great. And you got a coal train going by, you go, man, I need to get rid of that, and you don't have a clue. Now we calculated what it's going to take. Can we do it? Yeah, but we got really a lot of work to do to get it done. You're not just going to walk out there and throw some solar panels up and solve the world's problems. It's going to be a part of it, but we've got a lot more than that to it. And, okay, 2, advanced problem-solving skills, lay out a problem, break it into solvable parts. I talked about that. That allows stepwise solutions. Increase understanding of energy unit conversions and process of unit analysis. That's a little bit of part of the first one, but that's the avenue to get there. And your appendix in the back of the book is most useful for that, and I know you all Google things, but be careful when you do. Advanced research skills, find a relative data and conversions required to solve problems. Okay. Many of the problems as written the first semester I wrote them, I did not cite in the text where it was. I cited, well, we're in this chapter, this is where you'll find information on this problem. It got to be a little bit of a scramble for people, and I started to put more in there about, hey, use box 5.3. Take a look at it. That's along the same lines as this problem. Okay, or page whatever is a table, and you'll see the conversions or the data you need there. 5, clearly document the solutions. I think this is real important. For others, pursue correct spelling required. But you're out there as an intern, let's say, and they're really trusting you, and you're interning for a solar company out there, and you are involved in writing up a proposal for a customer. Well, a customer, if I'm a customer, I want to know that you know what you're doing. Like this doctor yesterday, she was good. You know, she gave me pretty good confidence she was going to get this thing back together as best as anybody could. You go throw out a proposal to somebody and you got a bunch of scratching down there and they ask about it and you're going back there, oh, wait a minute, it doesn't play well for the potential customer. It's real important. It's part of selling a business, selling work you do for business, or selling yourself. So anyway, that's a lot within those 5 statements. This is kind of logistics, up to 5 word problems. Each problem must clearly indicate the problem given and find it. And that's what I want you to do, okay? I think as part of the solution, and what I'd like to see when you write your problem document up, separate a given and a find section with all the units. Then go through your calculations, including conversions in units. 5 feet. What? 5 feet per what? Okay, you need your units. Often you get in a hurry, and I do it too. And you get in a hurry and you miss the 7 pounds per, or 7 kilograms per cubic meter, let's say, as a volumetric density, and you forget the cubic meter in there. And if you're getting into an involved problem, you get down the road a ways, you have a hard time solving it. If you continue to carry your units through, you'll know where you're at. And particularly with the good old mega, giga, 1,000, milli, often, and I was doing it last night, and going back and solving one of these problems, I had ton per gigajoule, and I had joules there, but it was megajoules. And I went ahead and ran it out because that doesn't look right. Well, I forgot to change the one to the other because I hadn't written it down so I could see it, basically. And then submit it in a Excel, Word, or you can do it in hand, but you got to scan it. And no phone photographs that don't work for grading. I had a couple of them submitted via photograph from my cell phone, and could see them good, but you can't mark them up and get them back. And when I did it, I would, take the time to go through and mark them up for you. Excel solutions must go to a separate tab showing calculations. If you know how to do that in Excel, you can go to another tab and do that. Okay, and then you should, as always, there's a participation board for those, and you can share your problems with each other and help each other out. And then there's a way to submit them as file names. That's very helpful to the grader for saving your document in the grading file and getting back to it again and whatnot. Okay? But you all can go there. Any questions on any of that jazz? Where are we at time-wise? No, we're good. Okay, so let's go here. Practice word problem that I'm on. There's a forum for problem set 1, so we didn't sign that. Let's go to, we'll step out here for a minute, and I'll show you what I'm talking about with a specific. Oops, you can still see that? I do that all the time. Okay. Now this is right off of Moodle. Here's assignment 2, problem set 2 as presented last semester. And it's up on Moodle as if that's what it's going to be, and it as yet is unassigned. And what week was this in? Last week or this week? This week. So it's coming up pretty soon. And he may modify it a bit from this, but I've given this go through as an example of what these things are like. And here's a little reminder of how to do that. 3 significant digits. Try to remember to do that. It's uncomfortable to go through and grade a document and you got a number out there that's 347.7778424. You don't need that. 347 works, And there is a test question on this next exam concerning significant digits. It's not a hard one, but do you understand significant digits, guys? From your other math, whatnot, okay. Rather than go there, this first question is pretty straightforward. And another part of what I decided could be done in this class, done in these problem sets to augment learning. A lot of time these tables in the book, when I read a text like this, I have a bad habit of writing the, and there's a reference to a table and I'll glance at it and keep on reading and don't really look at and understand the table. There are a lot of test questions, you probably already saw it in the other exam, from the tables. And being able to read these tables is helpful. They're laid out a little funny, and maybe you're all okay with it, but let's take a quick look at table 5.1, look what I'm talking about here. And this is a relatively easy, straightforward problem, or less. What page is 5.1? Oh, it's down there, isn't it? It's reserves. That's towards the end of the chapter, I think, isn't it? Mid to end. There it is, page 163. So let me go here, see if I can do this. Sometimes this doesn't work so hot. Oops, wrong one, sorry, dudes. There it is. Yeah. So Okay, so that table, let me get to the next page then. Where'd you go? There it is. Drives me nuts. Yeah. So look at that table 5.1, labeled coal reserves, annual production, and R to P ratios, okay, for selected countries. What's R to P? You know from your readings? And there's a test question on that. What's R to P ratio? Jesus. Sorry. R to P is, there.
Reserve to production.
Yeah, reserve to production ratio. So that's the amount of coal reserves divided by the production, all right? And what are the units on that ratio? Well, it's unitless, right?
Yep.
Or is it not? No, it's in years. My bad. If you look at the, look at the columns in the table, we've got reserves. First you got country. That's USA. You got reserves, and that's as 1,000 MT. What's MT?
Megatons?
Metric tons.
Tons? Okay.
Or 1,000 megatons. You got it.
Okay.
Yeah, I was thinking metric ton. The T is the metric ton. You got it right. Good work. But see how goofy that's written? When I first was in this class, it drove me crazy, and maybe I talked about it. You got reserves, and then you got, that's why I drew that line, slash 1,000 metric ton. For a long time, I had trouble reading that as reserves divided by 1,000 metric tons. It's not. It's just they just segment the title from the units. Okay. It's important to understand the units in the tables. So percentage, that's pretty easy. Percentage of world, and that's not really a part of this problem as percent. You've got annual production, again, that's as metric tons. And percent of world production, and so that's reserves. We're going to run out of room here. And then you've got your RP ratio. What are the units on RP ratio? Years. So in the USA, if you've got 238 metric tons of coal reserves, this was 10 years ago, basically 5 years ago, 2010, it'll say. 2009, says right in our table. And that's important to know. And I'm not going to deal with the percentages right yet, but that's another test question you'll end up having on which countries have the most coal. This table will be helpful, so is that map that's in your book. Annual production, 973 metric tons. Whoops, and I forgot a unit. There I go. I already forgot a denominator. Metric tons per year. I've had students in this problem get messed up with that. So to get years, how do we do that? We want year for 973, and we can do this. We can turn it around. That's the same as this, right? and we've got 238 metric tons in the country. So we got 238 divided by 973, but that doesn't look right. That's less than 1 year. We got a lot more than that. What have we done wrong here? What have I done wrong here? This 238 is 1,000 of them. So I can do this. See? It's 1,000 metric tons. And actually, when I was first looking at this, I had that all messed up. Got it? So that first table, that 238 is not 238, it's 238,000 metric tons. But to save all the zeros, they showed that in the heading for the units. And if you divide that out, it probably comes out to 245 years. Okay? That's how that table works. But this table, just at a glance, looks pretty simple. But once you get into the numbers and trying to make sense of them, you see that there's really not that much to it, but you got to understand what the units are. And the headings tell you what the units are. Okay? That's the lesson there. Let me do this for now. There it is. But all these tables are like similar to this. Let's go back to the problem. Okay, so there we're asked to go to 5.1, and we've been there. At current coal usage production ratios, the USA has how many years of coal left to extinction? Well, we just looked at that, didn't we? That is the definition of R to P ratio. However, then the problem asks you to go like, okay, if the USA was using coal or has production of coal like China's, how many years left would we have? You know, and if the USA were as current production and China's reserve, how many years would we have left? And then show your calculations. Okay? So you would do what we did here. Oops, I won't keep wanting to do that. For the first problem. But show your given and find. All right? First part of the problem, the second part of the problem, the third part. And to do these over, I'd segment those by A, B, and C to make it simpler. But that's not life either. You go into a situation at work or life, you've got way more information than you're going to need. But you got to sort through it. And I didn't really give you more information than you need here. And some of the problems we do. Follow that? We're good with that? Any questions? So let me go back to, do you want that up or the description of the problem?
Can you leave this up?
Yes, sir. Let me, but good time, yeah, I'm a good time to do the, pause the, or segment the recording, so let's do that.